Hello and welcome back. In this video we're going to look at another way to get intuition about the fundamental theorem of calculus, part 1. Let's take a look. So on the left side we've got this function f of t. This is graphed on a coordinate system where the x-axis is t, the y-axis is the function values. So we've got this random function here, f of t. And this is little f of t. And we're looking at the area under that curve from t equals a to t equals x. Now just to start off, we can write that area, which will be a function of x, and we're going to call that area big F of x. And the way we can calculate that area is by finding the integral from a to x of f of t dt. That's what the integral means. It means the area under that curve. Now what we're going to do is we're going to think, what happens if we move a little bit, if x moves a little bit to the right? So we're going to move x a little bit to the right and see what happens. Well, let's move specifically h to the right and see what happens. Figure out what rate, we're going to eventually try to figure out what rate the area is changing at. So we're going to move over a distance of h, an x value of h, or a t value of h to the right. And in fact, on here, I'm going to draw the h as well. So this is like x plus h right here. So we're moving t to the right by h. Now if we wanted to figure out how much area we added just now, well, it would be this shaded area right here. It would be the area under the curve from x to x plus h. Or another way you could figure that out is you could take the area under the curve from t equals a to t equals x plus h, which would be this whole area from t equals a to t equals x plus h, and then subtract off the area from t equals a to t equals x. And that would just get you the area in between. So this is big F of x plus h minus big F of x, where big F again represents that area out to a t value of x, whatever that is. Okay, so that would be the actual change in the area if you were to move your x value, or your t equals x, a little bit over to the right so that it's t equals x plus h. But let's look at another way of doing this. So let's approximate it using a rectangle. So we're going to move over a little bit by h, and instead use a rectangle to approximate this change in the area. So we're going to use that rectangle to approximate the change in the area. The height of that rectangle, let me use a different color for that. So the height of that rectangle would be f of x, little f of x, right? There's x. If we plug x into the function, we get little f of x. And then the width of this rectangle would just be h. So that the area of this rectangle would be f of x times h, little f of x times h. So if we ask the question, what is the rate at which the area is changing? In other words, what is big F prime of x? We're going to be able to figure it out using just a few steps down below. First, we're going to note that these areas are approximately equal to each other as long as h is pretty small, and in fact the smaller h gets, the closer these two areas on the left and the right are to each other. So this area, the actual area, change in the area compared with the estimated change in the area, are about the same. So these are about the same. Now we could take that's what the little squiggly equals are, about the same. So we could take the h, we could divide it to the left, and then to make them exactly the same, we could take the limit as h approaches 0. As h shrinks down to 0, the actual area is going to approach the approximated area. Right? These rectangles will be skinnier and skinnier, and they'll be closer to the actual area involved. So when we take the limit as h approaches 0 on both sides, well, on the left side we just have the limit as h approaches 0 of big F of x plus h minus big F of x all over h. That should look really familiar. And then equals the limit as h approaches 0 of f of x is just f of x. So on the left side, what we've got is the definition of the derivative of a function. In this case, the derivative of big F. So this is by definition the derivative of big F of x. So we're saying that big F prime of x is equal to little f of x. But big F itself was defined to be this area function right here. It's this integral from a to x of little f of t dt. So we could replace the big F of x with the integral, and out would pop fundamental theorem of calculus part 1. So here's where you can get the intuition that the rate at which the area is changing is equal to the value of the function at x. If you want to paint on a little bit more area, if you want to move over to the right a little bit and paint on a little bit more area, the amount of area that you're adding is equivalent to the function value right there. So it's equal to f of x. Little f of x, I should say. Okay, so thank you for watching this video, and see you in the next one.